This is topic 1.9 and 1.10 of AP Precalculus about rational functions under vertical asymptotes and holes. If you find this video helpful, share, like, and subscribe. Okay, let's recall a rational function is the quotient of two polynomials. Okay, just like this one, we've been using this representation of a rational function. Y is equal to f of x over g of x, where f of x and g of x are both polynomials. Since we are dividing by a polynomial, rational functions have restrictions on their domains. We know that we cannot divide by 0, so we must consider any x values where the denominator g of x is equal to 0 and restrict them from the domain. Now, these values will be the location of either a vertical asymptote or a hole in the graph. Okay, take note of that again. These x values, okay, that's going to be from g of x, which is actually your denominator, will either give you a vertical asymptote or a hole in the graph. Now, vertical asymptotes and holes occur when the denominator of a rational function equals 0. Okay, so look at that very carefully. Vertical asymptotes and holes both occur when the denominator of a rational function equals 0. So how can we distinguish between the two when working with a rational equation? Okay, vertical asymptotes and holes. A hole occurs when the factor in the denominator cancels out. Keyword, cancels out completely with factors in the numerator. Okay, so that's actually the keyword. A hole will be there. What about a vertical asymptote? A vertical asymptote occurs when a factor in the denominator again cannot cancel with the factors in the numerator. So the keyword in here is one is going to be completely canceling out and the other cannot cancel out. Okay, holes. Let's look at this example, f of x and g of x. If we're going to be looking at the denominator and the numerator, we can say that we can actually cancel these two. This one and this one is going to create a hole. Another thing is on the g of x, we can completely cancel this one, except that in here, there's going to be one factor x minus 1 be left. So if you're going to put these equations in a graph, specifically in how these two factors are being canceled out, it's actually going to look like this one, a circle. There's a circle in there. So that's how it looks like in a graph. Can also say that in this part, the graph is actually not continuous. Now, another thing that we have to remember is that uh, this hole can also be stated using a limit statement. So just like this one, limit of f of x as x approaches 1 from the left side. This is your left side. That negative side in there is going to be left side, and this is going to be your right side. Now let's look at the graph carefully. So if you're going to be approaching your function from the left side of 1. So this is your 1. Okay. From the left side of 1, if you're going to be coming from here, okay, so what value of y does it actually approach? It's not at, but it's actually just approaching. So we can see that it's going to be approaching 3. Now, the same also if we're going to be coming from the right side. So here, the limit of f of x as x approaches 1 from the right side, the plus sign means right side. So if you're going to be looking at this one, you're going to be going this way, approaching 1. Okay, this is our 1. And we're going to be ending up with the same y value, which is 3. Therefore, we can say that the limit of function as x approaches 1 from the left and 1 from the right is actually 3, which is the y value of the function. Now, let's look at vertical asymptotes. Okay, in our earlier studies, we said that vertical asymptotes can actually be found in the denominator. The numerator is going to tell you the zeros of the rational functions, while the denominator is going to give you the undefined values, and sometimes those undefined values, not only sometimes actually, but these undefined values is where you can also find the vertical asymptote. So look at f of x and g of x. So if you're going to be looking at this one, we can say that they are actually having an asymptote at x equal to 1. So if we're going to equate it to 0, okay, it means that x cannot be equal to 1. In here, there's still 1 in here. If we're going to cancel this one, and here there's still one in there down there, so it didn't actually completely cancel out, okay, the factors from the denominator in the numerator. Therefore, there is going to be a vertical asymptote in this case. Now let's look at and scrutinize the graph. Okay, so if you're going to be looking at the graph, our vertical asymptote in here is actually located at 1, this part. Okay, that is going to be our vertical asymptote at x equal to 1. So the graph above has a vertical asymptote at x is equal to 1. And after that, we also have to look at the limit statement for vertical asymptotes. Now, if you take note of what we are doing here, the vertical asymptote is actually the value of x that the function is actually approaching from left and right. It means that if you're going to start from the left side here, the left side, okay, of negative, sorry, of positive 1 here, this is your positive 1, right? And you're going to be going this way. So where does the graph go? Will it go up or will it go down? It actually goes down, and that's going to be the negative infinity of your f of x. Okay, let's do the same thing with the other side. If, say for example, we are coming from the right side, okay, this is the right side. So if you're going to be looking at the right side here, I'm going to be coming from the right side, and I'm going to approach 1. Where will my graph go? It actually goes up, and that going up is actually represents the values of your y, of y values going to positive infinity. For us to understand very well what we are discussing here from the very beginning, I'm going to lead you to our examples. Example 1. For each function below, determine the x values of any holes or vertical asymptotes. Okay, x values of any holes or vertical asymptotes. Let's look at letter A. So this is very easy because both are given as factors already. So here I can see that x plus 3 and x plus 3 are both numerator. They're going to be canceling out, completely canceling out. It means to say that I have a hole at x is equal to negative 3. Now, if you're going to be writing what is left out in here, you have x minus 2 on the numerator and you have x minus 5 in the denominator. This factor is now going to serve as your vertical asymptote. Therefore, your vertical asymptote here is located at x is equal to negative 5. Okay, let's go for letter B. Here, this is very interesting because I can easily see that I can cancel out here. This is 2, x minus 2 and x minus 2 are actually canceled out completely. Therefore, I can say that the whole is at x is equal to 2. Okay. Look at the other factor. In here, I can also see that x plus 1, and there's going to be another one in here. So there's going to be one more down. So it didn't completely cancel out. So if I'm going to rewrite what is just being left out in here, is just 1 over x plus 1. Okay, and our denominator is going to be our vertical asymptote. So our vertical asymptote in here is going to be x is equal to negative 1. Okay, let's look at letter C. This is very nice also because I can see that the denominator needs a little bit of fixing. So here I'm going to factor out our denominator. X is going to be x squared plus 4. So after factoring out already, all I can see is that I don't have anything to cancel on the numerator and the denominator, but I can see the value of x. If I'm going to say therefore my vertical asymptote here now is just located at x equal 0. Now what about this one? Now I would like you to look at this one. If you're going to equate this, x squared is equal to negative 4 and get its square root, that's going to give you plus or minus square root of negative number. Now we have been studying already about imaginary numbers, and we know that this is going to be giving you 2i, okay? Which they are imaginary in nature, therefore they don't really appear in your graph. Okay, so let's look at the next one. So the next one, it says example number 2, write a left and a right limit statement as x approaches 2 for each of the following functions. Okay, so all I can see in here is that they're asking us to look at x approaches 2. Okay, so we cannot put anything except approaching 2. So it means to say that we're going to be writing this way, x approaches 2. So that's what we're going to be doing in here. Now let's look at letter A. Do we have anything to cancel in here? I have nothing, but I can see that I have a vertical asymptote at x is equal to 2. Okay, so since 2 is just my critical point in here, so I'm going to look at what is exactly happening at 2. So in this case, I will just get a value that is near 2 and above 2. So I can say that I will just get maybe 1.99, yeah, or 1.9 maybe. And here I'm going to just get 2.1, something above 2 or below 2, but not exactly 2. So now I'm going to get all my values that I just chose in here, and I'm going to put it or substitute it into the equation. So say f of 1.9, so that's going to be give me 1.9 minus 1 is going to give me a positive number. 1.9 plus 3 still a positive number divided by 1.9 minus 2, that's going to give me a negative. So to solve this one, the signs, it's going to just give me a negative sign. So on this side, it's going to be a negative 1. What else? If I'm going to put f of, let's say, 2.1, okay? That's going to be 2.1 minus 1. That's going to give me, of course, a positive. The other one is going to be 2.1 plus 3, still a positive. And then 2.1 minus 2, it's still going to give me a positive. So evaluating that, it's going to give me a positive value. Okay. So now if I'm going to be looking at again my line graph in here, this is actually the left side of my 2 and this is the right side of my 2. So what is happening in here is that if I'm going to write the limit statement in here, say the limit of f of x as x approaches 2 from the left side here, from the left side, then what is happening in here? I can see it's actually going to negative infinity. Yeah, it's negative infinity. Okay, if I'm going to also write my limit statement on the right side, look at what's happening on the, it's going to be a positive infinity. So the limit as x approaches 2 from the right of f of x is equal to positive infinity. Okay, so let's look at letter B. This is very interesting again because they already factored out for us. But let's observe what can we see in here. So we can actually cancel x minus 2 and that's going to give us a whole at x is equal to 2. So if I'm going to write my limit statement, say limit as x approaches 2 from the left side of our f of x that is left is just this one, right? This is the only one that's left after we canceled out. So we're going to write that one instead of say g of x, say of x plus 4 all over x minus 3. So we're gonna stuck in here, but what we're gonna do is let's get that value of 2 and substitute it in there. Okay, so for us to see what's gonna be the limit of the function as it's going to approach 2 from the left side. Okay, so let's do that. So that's going to give you 2 plus 4 over 2 minus 3. So this is going to give me 6 over negative 1, or simply negative 6. So that is the limit on the left side. Now, what about on the right side? Using the same concept, x approaches 2 on the right side of x plus 4 over x minus 3. So I'm going to do the same thing again. I'm going to substitute that in there. So this is going to give me 2 plus 4, and this is going to give me 2 minus 3, which is going to give me the same yield, negative. So it's going to give me the same result, which is negative 6. Now, I would like you to just take note. What happens in here is actually, this 6 is actually your y value, true? So if you're going to be looking at the coordinates of the whole is actually located at 2, negative 6. We're going to learn more about that later. Okay, so let's look at letter C. Okay, h of x. So what did you first notice in here? Okay, I can see that I can cancel out x minus 2 factor on the numerator and one more x minus 2 in the denominator, and that's going to just leave me one more x minus 2 in the denominator. Okay, with that said, it means to say that x minus 2 down is not a whole, but it's going to be a vertical asymptote. Okay, a vertical asymptote at x is equal to 2. There's actually one more vertical asymptote in here, but I'm not interested so much of that. I'm so much interested with this because there was one common factor on the numerator, and I would like to see what's exactly happening around this one, okay, around that vertical asymptote. So I'm going to draw our number line here, and we're going to put 2 in here. Now I need to choose one number from the left side of 2, maybe 1.9, and one more number on the right side of 2, which is going to be maybe 2.1, because that's the best choices we have got here right now. Now I'm going to substitute it in the full equation. So let's say 1.9. So on this 1.9, if I'm going to substitute it on the numerator, that's going to give me a minus. So 1.9 minus 4 is going to give me a negative, and 1.9 minus 2 is going to still give me a negative. Then 1.9 minus 2 is going to give me a negative, but remember it is squared. So negative squared is still going to give me a positive. Okay, so this is positive, and x, or 1.9 minus 1, is still going to give me a positive. So all in all, this is going to yield a positive. So on this side, it's positive. Now let's substitute 2.1. Okay, that's going to be here. That's going to be f of 1.9. Here is going to be your f of 2.1. Okay, so let's look at it. If I'm going to say 2.1 minus 4, that's going to give me a negative result. 2.1 minus 2 is positive. Okay, down below, it's going to give me 2.1 minus 2. It's going to give me actually 0.1, but we're going to square that, so it's going to give you a positive result. And then 2.1 minus 1 is still positive. So a total of this is going to give you a negative, because there's one negative in there. Okay, so on this side, the right side is going to be a negative. So if I'm going to now write the limit statement of the function as x approaches 2 from the left side here, from the left side, then of f of x, then what's happening here is going to be approaching positive infinity. Now writing it on the right side, this is our right side, 2.1, x approaches 2 from the right side of f of x, what is actually happening here is that it's actually approaching negative infinity. Okay, so that's the answer to that. Okay, let's go to the next. Example number 3. Write an equation of a rational function with the following limit properties. I guess this is very interesting because earlier we have been asked to really write the limit statements given a function. This time is the reverse. We are given the limit statements and we're going to get the function. The limit as x approaches 3 from the left of f of x is equal to 5, and the limit as x approaches 3 from the right side is 5. This is going to tell me that this is actually a hole. It means to say that I've got a hole at x is equal to 3. Okay, what else can I infer here? The limit of f of x as x approaches 1 from the left is negative infinity, and the other one is the same one approaching 1 from right. It's going to be positive infinity, so they are actually opposite. It means to say that I actually have a vertical asymptote here. I have a vertical asymptote at x is equal to 1. Now, if we're going to write our f of x, remember a whole should have at least one in the numerator and one in the denominator. So we're going to write that one. So the factor in here, x is equal to 3. It's actually going to give you x minus 3, 3 in the numerator and x minus 3 in the denominator. Why? When you're going to be canceling this out together, it's going to give you whole at x equal to 3. Then the next thing we're going to look at is the vertical asymptote. Remember, vertical asymptote is actually down under. Okay, it's going to be in the numerator. And if I'm going to put that in its linear factor, it's going to give me x minus 1. Okay, so according to the limit statements that we have just scrutinized today, this is the possible function of these limit statements that we have just read this time. Okay, letter B. The limit of f of x as x approaches negative 2 from the left and also from the right is 4. Okay, so it means to say that this is going to give me again a hole at this point. So the hole is actually located at x is equal to negative 2. Another thing that I can see in here is that the limit of f of x as x approaches negative 1 from the left is positive infinity. And on the right, look at this one, very nice. It's going to be positive infinity. So what does it tell me? It tells me that it's going to be, the multiplicity is going to be even. Okay, so let's see. The vertical asymptote, therefore, in here is located at where? Vertical asymptote is located at x is equal to negative 1 here. That's the negative 1. Okay. So the possible function in here that we can create, so since we have a hole in here, the linear factor of x is equal to 2 is just going to be x plus 2 on the numerator and x plus 2 again on the denominator. Now, earlier I said, look at this one. The limit of the function as x approaches negative 1 from both right and left is the same infinity. So it means to say that if I'm going to write this one, x plus 1, then it's going to be uh, an even degree. Okay, so reason why, because if you're going to be looking at, say for example, the f of x is equal to 1 over x squared. Okay, actually look at the degree is 2, so normally they actually go up this way. Now if you're going to be looking at also your function, f of x is equal to 1 over x, which is the parent function of that rational function, you can actually see that the degree in here is odd. Okay, so one is going to be going down and one is going to be doing this way. So one approaches negative infinity, and the other one approaches positive infinity. So that is the case of this letter B. Okay, so if you can see that these are both the same, it means to say that the degree of the numerator is going to be even. Therefore, we put x plus 1 square. Okay, let's go for example number 4. Sketch a picture of rational function that has the following properties. Okay, letter A. F of x has a whole at x equal 1. Okay, it has a whole at equal 1. As x approaches 4 from the left, 4, it means to say that's going to be my vertical asymptote. F of x increases without bound. It means to say it's going to give you a positive infinity. As x approaches from the right, f of x decreases without bound. This is going to be negative infinity. So if we're going to graph this, a rough sketch, okay, so let's say here, 1, remember 1, you have a hole at 1, and it says that the vertical asymptote is at 4. Here it says here, so 1, 2, 3, and 4. Yeah, okay, so this is going to be your vertical asymptote, and it says that as x approaches 4 from the left, f of x increases without bound. Okay, it means to say that it's going up because it's going up, and then as x approaches 4 from the right, f of x decreases without bound. It means to say that it's going to be, this is my vertical asymptote, yeah? So it's going to be going down this way. So roughly the sketch is going to be like this. Now let's not forget that there is a hole here. There is a hole at 1. Okay, there's a hole at 1. So we have to put the hole at 1. So say for example, I'm going to be doing it this way. Maybe there's a hole somewhere here, and it's going to go up this way. So this is just a rough sketch of what is being described in this item. Okay, let's go for letter B. Okay, g of x has holes at x equal negative 2 and 3. 2 holes. As x approaches negative 1, okay, here this is our vertical asymptote. Okay, so vertical asymptote is actually located at x is equal to negative 1. Okay, g of x, this is the left side of g of x. It decreases without bound. It means to say it's negative infinity. And on the right side of that negative 1, g of x also decreases without bound. So they are both decreasing in nature. Okay, so let's write that part. Let's sketch it. Okay, so first we are going to say that negative 2, let's go for our vertical asymptote first. Okay, that's going to be negative 1. So that's going to be our vertical asymptote. Okay, next is going to be, it says a hole at negative 2. Okay, a hole, let's say, so let's write negative 2 in here. Okay, 1, 2, and 3. Maybe that's going to be 3. So remember that in 2 and 3 there are holes in there. So let's see. It says that as x approaches negative 1 from the left, it's actually decreasing. Okay, so it can be going this way. So it's going to decrease this way. Yeah. And at 2, somewhere at 2, it's going to have a little circle in there. Okay, that is actually the hole. Okay, and same also with the right side. G of x decreases without bound. So it means to say that from here, I'm going to just pass through here maybe. Yeah, there's something like this. And maybe yes. Hold on, that's very inaccurate because my asymptote is somewhere here, and I'm actually very far already. So somewhere something like that. Okay, okay. So it's going to be this way, but at 3, it's going to be a hole. Okay, so this is the rough sketch of our graph according to these properties of limits. Okay, so that's all for this lesson. So this is all about topic 1.9 and 1.10 on AP Pre-Calculus regarding rational functions about vertical asymptotes and holes. If you find this video helpful, share, like, and subscribe. Thank you very much.